In this video, we are going to be doing a Unit 2 Forces FRQ on a flying pig. The flying pig is basically when we have this pig with wings that goes in a circular motion in a state of being attached to a string that is attached to the wall. So it is going to make a conical shape when it revolves around that circular path. And what we are asked are to draw a free body diagram for the pig when it's at rest, and then a free body diagram for the pig when it's in flight. We want to find the pig's speed in terms of theta, m, l, and g, and we'll show our work. So, when the pig is at rest, we are going to have the summation of forces in the y direction is going to be equal to be 0. Ft is going to be acting up, and we're going to have the weight force of the pig acting downward equal to mg. So Ft minus mg is equal to 0 because we're in vertical equilibrium. Now, when we're moving in a horizontal circle, it is going to create the conical pendulum. So we have that the force of the pig is going to be at an angle towards the pivot, and we have the weight force that is going to be acting down. Now on our sketch here, not on the official free body diagram that we create, when you create the FBD, you only want to include new forces. You don't want to break things up into components. But we can label here, this is force of tension. This is force of tension in the horizontal direction. This is the force of tension in the vertical direction. So, the angle theta is going to be made with the string here and also there. But the true theta you want to represent is this theta. This is another angle. We won't be using that. So, now if we use our right triangle trigonometry, we get r is equal to L sine of theta. This is our length of our string. So if we dissolve it into components, we can see ftx is going to be ft cosine of theta. Since this is going to be, or no, this is going to be ft cosine theta. This is the adjacent side, and this is the hypotenuse. And then for ftx, we get that this is our opposite side, and that's our hypotenuse. So sine relates to 2, ft sine of theta here. Now we can do our Newton's second law vertically. So because we know that the pig is not going to have acceleration up or down, we just have the horizontal circular motion. So that means that the summation of forces in the vertical direction is equal to 0 because ay will equal to 0. So that means for our vertical forces, we have Fty acting up and mg acting down. That's equal to 0. So we know that Fty was ft cosine of theta. What we can do is add mg. And you can see clearly that ft cosine theta is just equal to the mass times the gravity. If you solve for tension force, you divide both sides by cosine theta. So you get that the force of tension is equal to mass times gravity divided by cosine of theta. Now after this, we can apply Newton's second law in the horizontal direction. So we know that when the pig is moving in a circle, it's going to have a inward centripetal force, which is causing it to maintain its circular motion. So this component is going to contribute, ftx is contributing to AC, is contributing to your net centripetal force inwards. Fc is not a new force. it is net force inward. That's not a new force. You wouldn't draw that on an FBD. So we can write our summation of forces in the horizontal direction is equal to the mass times acceleration, that is centripetal. We know our centripetal acceleration is v squared over r. Simply substitute this into your equation. So you get the summation of forces in the horizontal direction is m times v squared over r. So we see that the only horizontal force is going to be that horizontal component of tension, right? That we saw, Ftx. That's the only force in the horizontal direction. So we have Ftx here. Ftx is equal to Ft sine of theta. Now, what we can do next is substitute our r is equal to L sine of theta. So with this, we substitute this in right here. We have Ft sine of theta is equal to m times v squared over L sine of theta. So now from above, we already had that Ft is equal to mg cosine theta. So we'll take that expression here and substitute it in for Ft over here, giving us mg cosine of theta times sine of theta is equal to m times v squared over L sine of theta. After this, we see mass is present on both sides, so you can cancel that out. Then we have g cosine theta, sine theta, is equal to v squared over L sine of theta. After this, we can multiply both sides by L sine of theta so that we can isolate our v. If we do this, then we have v squared is equal to g L sine squared theta divided by cosine of theta. After this, you just take the square root of both sides, and you get that your speed is equal to sine theta times the root of g times the length of the string divided by cosine theta. So, in conclusion, we see that for this pig with no mass, the weight and the centripetal force requirement, they're going to be proportional to our mass. So they cancel out from our final expression over here. So we can see the speed doesn't depend on mass.